Before leaving the section on brushless DC motors, there's one disadvantage that I should mention that you should be aware of, and that is when you're commutating the current out of one coil and putting it into another coil, there's a little bit of torque ripple that's associated with that. It would be really nice if we could, symmetrically bring down the current in one coil while we're gently ramping up the current in the other coil so that we don't get this little torque perturbation, but that is almost impossible to do. Now, for a lot of applications, like let's say fan loads or maybe some other load that would be a high inertia load, this little bit of torque ripple really doesn't amount to much, and it's not even worth worrying about. But in some other applications, like for example electric power steering, any torque that the motor is producing, any torque ripple, is brought out to the steering wheel and is actually amplified by the radius of that steering wheel, and your fingers can actually feel any little torque ripple. So for those kinds of applications and others like them, we need to find another topology, another motor topology that has very, very low torque ripple, and that's this next motor that we're going to talk about. Here we see the cross section of the stator of a different motor, where instead of having salient stator poles that actually have wires wound around them, we actually have slots in the stator structure, and we can bury the stator coils down inside those slots. Now if you notice here, look how smoothly the magnetic field is rotating. And not only that, but look how smooth the transition is between the north pole and the south pole. This is clearly not similar to a brushless DC motor where we had, the magnetic pole would advance 30 degrees very abruptly as we commutated the machine. No, in this case you see it's a very, very smooth rotation and also a very, very smooth gradient. And if you stick a rotor inside of this kind of a stator structure with this kind of magnetic field, it will try to follow that magnetic field very, very smoothly. So the question is, how can we create a motor that has this smoothly of a rotating magnetic field? And that's going to be the subject of the next few slides. Let's take a look at the windings of this machine, and we'll start off with phase A here on the left. Now you notice that instead of the windings being restricted to a specific stator pole piece or a specific spatial region on the stator, the windings are actually distributed around the circumference of the machine. And another thing that's interesting is that distribution is not even. In other words, it's a sinusoidal distribution. So let's start over here at angle equals 0. We have smaller circles which represent fewer or sparser turns in that section of the stator. But as we move up to 90 degrees, we see a larger circle here, which indicates that the winding density in that area is much more heavily populated. So if we pass a current through this winding, through this coil, and you can see here that the current is going into the page on the bottom conductors and then coming out of the page on the top conductors, what that will do is that will create a magnetic axis for that particular phase, which is shown here along this horizontal axis. Now for phase B, we're going to take that same winding distribution pattern that we see in phase A, and we're going to copy it and then paste it back into the stator frame on top of phase A. But before we paste it, we're going to rotate that distribution pattern by 120 degrees as shown here, and then we put that back into the stator frame, and that becomes the windings for phase B. And you'll notice that because of that spatial shift of that winding distribution, that the magnetic axis for phase B is also going to shift by 120 degrees. And then we do the same thing for phase C, one more copy and paste, except once again we shift by yet another 120 degrees and then paste those windings back in, and they become phase C. So if you look at the bottom diagram here, you see an example of this where you have a stator frame with all three windings coexisting in the slots of that stator, and each magnetic axis for each of the phases is represented by the blue vectors. This slide tells a wonderful story, and I hope you enjoy it as much as I do. Let's pump some AC currents into each one of these windings. So as the current is going from positive to negative on each winding, it's going to create this pulsating magnetic field along the respective magnetic axes for each one of those phases. Now to make it more interesting, let's phase shift the currents by 120 degrees with respect to each other. And that means that those magnetic vectors are going to peak at different times. Now here's where the magic happens. You see, the rotor doesn't care what phase caused what magnetic flux. All it cares about is what is the total magnetic flux seen in the air gap. And if you take each one of those vectors, those magnetic vectors, and you add them together vectorially as shown in the bottom right space vector plot, you'll see that the resulting vector is rotating. This is the epiphany that Nikola Tesla had in the late 1800s when he invented the AC induction motor. He realized he could create a rotating magnetic field without any mechanical device, without any brushes or any commutator to do that. So as far as the rotor is concerned, it looks like the resultant vector as shown on the bottom left-hand side over there, which is actually rotating. Now we know that that physically is impossible, that we have stator coils that are actually fixed with respect to the stator. But the rotor doesn't know that. The rotor thinks that there's just one stator coil, not three, and that stator coil is actually rotating. So you can see that by exciting this three-phase machine with three-phase currents that are 120 degrees out of phase with each other, we can create this beautiful, smoothly rotating magnetic field that we need in order to have very, very low torque ripple. This slide, in fact, is at the core of the operation of every three-phase AC machine. As we saw on the previous slide, by applying just the right ratios of A, B, and C phase currents, we can create a current vector, or an MMF vector, to be at any angle that we want it to be at. So the question becomes, what angle should we shoot for? To answer that question, let's take a look at the chart in the upper right-hand corner of this slide. And here I've actually plotted the torque produced by a permanent magnet three-phase machine as a function of the angle between the rotor flux and that current MMF from the stator. Now you see at 0 degrees, in other words, when the current MMF vector is right on top of the rotor flux vector, there's essentially zero torque. But as we get out to either plus 90 or minus 90 degrees, we see that at that point we actually get the maximum amount of torque for a given amount of current. In other words, that's the maximum torque per amp angle. So it makes sense that in most cases what we should shoot for is to try to orient our stator current MMF vector to be at 90 degrees with respect to the rotor flux. If I can achieve this, then the torque equation at the bottom of the slide applies. And that indicates that the torque on a three-phase permanent magnet machine is proportional to the product of the rotor flux times the component of the stator current vector, which is at 90 degrees with respect to that rotor flux vector. To control the torque on the machine, I don't change the angle of my stator current vector with respect to the rotor flux. I always leave that at 90 degrees because that's where I get maximum torque per amp. Instead, I regulate the amplitude of the stator current vector. When I do this, I'm actually doing something which is called field-oriented control. In other words, I'm orienting my stator current vector to be properly aligned with the rotor flux to give me some maximum performance. And in this case, I want it to be at 90 degrees because that's where I get maximum torque per amp. So to do this on a digital processor, the process would go something like this. I'm going to get an interrupt on my processor. I'll go into the interrupt service routine. And the first thing I want to do is measure the rotor flux angle. Because once I know the angle that the rotor flux is at, then it becomes simply a matter of calculating the right values for phase A, phase B, and phase C current to create a stator current vector which is 90 degrees with respect to that rotor flux angle. I then apply voltages to the windings of the machine in an attempt to regulate the currents to be the desired values that I just calculated. After I do that, I exit the interrupt service routine, and then maybe 100 microseconds later I get another interrupt. By this time the rotor has moved to a different angle, so I need to read that new angle and then recalculate my current values again. I do this over and over and over, and that is the process of field-oriented control.